In this lecture, we will demonstrate a two-tailed hypothesis test for the population mean, where we know the population standard deviation sigma. Again, we will follow either the p-value or the critical value approach. For the p-value approach, we must compute a p-value which is double the area that we get in step 2. At times, this approach for a two-tailed test can be a little confusing using the p-value approach. My preference is the critical value approach, but you need to be able to do both. And the rejection rules would be the same for this p-value approach for a two-tailed test if the p-value is less than or equal to our level of significance. Because we are working with two tails, we need to double the p-value to compare it with alpha. Using the critical value approach, which is a little more intuitive, we will calculate both a positive and negative z critical value. We will then compare that to the z test value for alpha over 2. Let's do an example. Consider a production process, which is a great application for hypothesis testing. We are assuming that the process is equal to the aim of 6 ounces, and we take a sample size 30. The sample yields a sample mean of 6.1 ounces, and we know the population standard deviation to be 0.2 ounces. Now, at first blush, if the process is to be controlled right at 6 ounces exactly, and we get a sample that's 6.1, your first conclusion might be the process is out of control. But we can determine that with a hypothesis test. We'll do this test at the 0.03 level of significance, or a 97% confidence coefficient. As the assumption is that the population mean is equal to 6, that defines our null hypothesis. Mu equals 6, and our alternative is the population mean does not equal 6. We're working with a significance level of alpha 0.03. So to calculate the test statistic, we take the sample mean 6.1 minus our hypothesized mean of 6 and divide it by the standard error of the mean, which is sigma over the square root of n. We come with a z test value of 2.74. For the p-value approach, for z of 2.74, we end up with an area in one tail of 0.0031. We need to double that to 0.0062, and then we compare that p-value to our sigma of 0.03. Since our p-value is less than the significance level, we reject the null hypothesis. In other words, there is not enough evidence to infer that we are out of control. It's frequently easier to understand a hypothesis test if we draw the normal distribution and the critical values. This shows that the p-value, which is double 0.0031, is less than the significance level of alpha. Now, if we were to actually compare half of the p-value, 0.0031, it shows that it's also in the extreme tail of the distribution beyond the critical point. Therefore, we reject. Using the critical value approach, we've already determined the z test value, so we need to determine the critical z value. So for alpha over 2, for a two-tailed test, in other words, we have to split that significance level half in each tail. So we have alpha over 2 of 0.015. From the z distribution table, we find that that's equivalent to plus or minus 2.17. So we will reject if our z-test is either less than negative 2.17 or greater than positive 2.17. We see that 2.74 is greater than that, and therefore we reject the null hypothesis. This diagram of the normal curve shows the result. Again, for a two-tailed test, we have to use alpha over 2, the significance level over 2, to determine our critical z-value. While not used often, we can also use a confidence interval approach to a two-tailed hypothesis test. We develop a confidence interval around the sample mean using the same data as we did in Chapter 8. If the confidence interval contains our hypothesized value of the population mean, then we cannot reject the null hypothesis. We must assume it's true. Following that procedure for this example, we find a confidence interval of 6.1 plus or minus 0.079. Because our hypothesized population mean of 6 is not in this interval, then we cannot reject the null hypothesis.